So I'm here with the higher papers of all the questions, 6.5 and 6.6, and the equation sheet, a little bit bigger from the foundation, a couple more equations, and you've got these prefixes here. I'm going to put that down there because I might need it. First question, a class of students used 50 six-sided dice to model radioactive decay. Each of 8 groups gathered data and were added together. Describe a method used to collect this data. Well, first of all, you're going to roll some dice, and then you're going to pick a number. So dice with a certain number facing up are removed. So in the one we did, we picked number 1s because it was easy to identify. So we're going to remove those. We're going to count the number removed, the number of remaining dice counted. So we're going to count the remaining, and then the remaining dice are re-rolled, and then we start the process again where you count the numbers and you take them away. So for 3 marks, you want something along these lines, okay? Maybe not bullet points, but I've just tried to keep it simple there. So the dice are rolled, you pick your numbers, you remove the numbers, and then you re-roll. You record the number remaining, you re-roll. And then they've obviously gathered a set of results here. But I think we're going to have to plot. Let's have a look. Yes, we did. So I plotted them. I had to choose my scale. So I went up in 50s because I got to use half the paper. And I went up in just ones on the bottom. They've given me the axes, so I don't have to write in the axes, but I did anyway. And then the experiment is modeling the process of radioactive decay. Which important quantity relating to radioactive decay is estimated from the graph? We're going to estimate half-life. That's what these graphs, these decay curves are used. They're for half-life. That's what they're used for. I'm going to maybe keep that out a little because I might need it. Use a graph to estimate the quantity. Estimate this quantity. So obviously the quantity meaning half-life because they didn't want to give you the answer there because you had to give it there. So we're estimating half-life. I said 3.8 rolls. You can get away with decimals even though a roll is a roll or a throw is a throw. You can, because it's continuous data, you can get away with decimals there. So what I've done to estimate my half-life, I've begun with 400 dice, and then when I get down to 200 dice remaining, that is my half-life. I come across, I come down, and I've said 3.8 there-ish. Okay, you can go half of that again if you want to check, so 100, and then you can get across here. It's going to be like 7.5, then minus 3.8. It's going to give you a similar half-life. The distances between each are going to be very similar. And then the last question, explain how the results would be different if 12-sided dice were used instead. Well, it's taken my odds now from 1 in 6 to 1 in 12. So the probability is lower, therefore it's going to be a longer half-life. There's going to be less dice decaying each time, and your curve would be less steep. It would be sort of going above that line. So that's that question. Next question. Again, a lot of information. I'm going to see what the question is. State the number of protons in the nucleus of technetium. Well, if I have a look, it's giving me technetium 99. Has it got this? Well, it's element 43. So it doesn't actually give me anything in this question. But if you know it's element 43, it means it's got 43 protons. So if it's the 43rd element in the periodic table, so like hydrogen's the first element, it's got 1 proton. Helium's the second element in the periodic table, it's got 2 protons. Lithium's the 3rd element, it's got a proton number of 3. So that's where I've got that information from, even though sometimes they give you it, they give you a big number and a small number. They haven't in this case. It's a higher paper. 2 types of radioactive decay are mentioned in the text. Name the other types. So which ones are... So they've mentioned beta and they've mentioned gamma. So I've mentioned alpha. And for my second mark, and state what it is. Well, it's 2 protons and 2 neutrons. It's a helium nucleus. Okay, either one of those for your other mark. The initial activity of a sample of technetium is 99. Of technetium 99M is 5 times 10 to the power 4. So that is just... that's just 5 with 4 zeros after it. That's 50,000. Okay, if you wanted to simplify that, you could write it as 50,000. So it's 5 and then 0000. That's all that times 10 to the power 4 means. Calculate the activity remaining after 2.5 days. Well, it's got a half-life of 6 hours, it says there. So I've got all this information. Remember, if you can't find the information, always go back. It's probably going to be somewhere. And I need to see now how many hours I've got in 2.5 days first, before I can, because I'm dealing with hours here. So I've said 1 day equals 24. I know that looks like 27. 2 days equals 48. So 2.5 days equals 60 hours. So I've worked out how many hours I've got in 2.5 days. Well, let's see how many half-lives I've got. If a half-life is worth 6 hours, let's see how many 6 hours goes into 60. Well, it's going to be 10 half-lives. Now, I can either do the long way, and there's nothing wrong with doing this. I can start with 50,000. Half of 50,000 once is going to be 25,000. And then half of that again is going to be 12,500. Okay, and I can do it that way. And there's nothing wrong with that way. You're going to come up with the same answer. But there is another way we can do it. We can see how many, because what you're saying is half of 5 times 10 to the power 4, which is 50,000, is just 50,000 over 2. Now, 2 to the power of 1 is just 2, and then 2 to the power of 2 is 2 times 2. And then 2 to the power of 3 is 2 times 2 times 2. And we can do it like this. To save time, we can actually say, well, if I got 10 half-lives, 2 to the power 10, how many times does 2 to the power 10 go into 50,000? And it comes out with the same answer. It's just a short way to do it. Or you can do it the long way. You can actually write out 10 arrows and keep half in it. Maybe I would recommend that method because unless you're really good with your maths, you can get confused there. But it literally is, it's the same thing. So 2 to the power 10 is just 2 times 2 times 2 times 2, etc. And you can see how many times that goes into that. And then it says technetium, the isotope of technetium with the longest half-life is technetium 98. And it's got a half-life of 4.2 million years. So it takes 4.2 million years for half of it to decay. In 1952, technetium 98 was detected in a red giant, which are billions years old. Explain how the discovery of technetium 98 in these stars added support to the theory that heavier elements are produced within stars. Well, it's 2 marks, a bit of a tricky question, but really any technetium 98 initially present in the star would have all decayed. So they must be made later in the life cycle of the star, because like I say, it would have all decayed. We're talking about billions of years, and the fact that we can detect it, and it's only got 4.2 million years, and even though that seems like a really long half-life, it's not compared with the life span of stars. So it must have been made later on in when you get those stages in the life cycle of a star, such as supernova, and then they collapse. They become red giants. They become a red giant, and then they explode, and then they either turn into a neutron star or black hole or a white dwarf, whatever, depending on the size of the star. But these heavier elements are going to get made in that later stage. I mean, for 2 marks, a lot of work there, I think. But there we are. It is a higher paper. And then another question here. So we can clear our minds and go on to the next question. Isotopes of iodine. They can be used to study the thyroid gland in the body. A small amount of isotope is injected. So it's got 3 here. The 3 isotopes that could be used. So notice they're all isotopes because they've all got the same small number, but they've all got a different number of neutrons. They've all got a different mass number. So the first one's got a half-life of 13.22 hours. Second one's got 8 days, and this one's got 13.2 hours, respectively, means in that order. Answer the following questions in terms of numbers of particles. Compare the structures of the nuclei of this one and this one. Well, I've said they both have the same proton number, or number of protons, but this one, iodine 131, has 8 more neutrons than 123. And you can do that easily by working out 131 minus 123 is 8 more neutrons. The nucleus of 131 iodine decays into xenon by giving out beta and gamma. So sometimes you get beta and gamma. Remember, gamma is just a fast-moving particle, so it's not going to be any particles involved. What is beta radiation? It's a fast-moving electron emitted from the nucleus, or fast-moving electron from one mark. Complete the equation. So this time, slightly different from the foundation ones. So this side has always got to equal this side. So I've said something plus 0 is going to be 131. Well, that something is 131 plus 0 gives me 131. So the mass number is always the same in beta decay. But we're gonna gain a proton there. So 54 plus minus 1, which is the same as 54 minus 1, gives me 53. And then we don't have to worry about this gamma decay because there's no particles. The isotope 123 iodine decays by gamma emission. Explain why it is better to use these ones as a medical tracer. Well, I've said it's got a shorter half-life, so 13.2 hours compared with the 8 days, and it's less ionizing because it's gamma. So explain why it is better to use than these. So gamma decay, yeah, these are beta decays, so they're going to be ionizing by a charge of 1 because it's an electron. It's going to be looking to pick up a proton. You really don't want that inside you, okay? Gamma decay is what you want, and it's easily detected as well. Continue on the same question, so I'll leave that out just in case there's information we need. Iodine 131 has a half-life of 8 days. Explain what this means. Well, that's asking you for 2 marks. What is half-life? Well, it would take 8 days for the mass or the activity or the number of parent nuclei to decay or to reduce by half. Okay, there's many ways you can say it, but basically it's the amount of time. 8 days is the amount of time it takes for this element to decay by half. Following the nuclear power station disaster in Japan, people living in the area were given a non-radioactive iodine 127. Supplement tablets reduced the intake of iodine 131, blah, blah, blah. What's it really asking me? Calculate the length of time that people had to take the supplement before the activity of iodine 131 reduced to approximately 3% of its original value. So we're dealing with an 8 days of a half-life. We're dealing with 3% it needs to get down to. So I've gone from 100% to 50 to 25 to 12.5 to 6.25 to 3.125. And it says there approximately, so I think that's fine. If you had done another one, it'd be fine. But I've got 1, 2, 3, 4, 5 half-lives to get down to 3%. So 3 half-lives at 8 days. 5 half-lives at 8 days is going to give me 40 days. And I don't know why I've written 80 there. That is totally wrong. That needs to be changed to 40. It's definitely 40, and I checked on the mark scheme. There is 40 days. So that one's right. I don't know why I've written 80 there. I must have had a moment.